Good morning, friends. Welcome back. Okay, today I'm going to deliver the ninth lecture. Okay, in previous lecture we start the numerical on first law of thermodynamics part 1. Okay, I'm going to divide this numerical in number of videos. Okay, I'm going to make the videos of the short span around 20 minutes videos. So we can from that 20 minutes span of that video, we can easily understood hardly 2 or 3 numericals. Okay, so you can easily understood the concept thoroughly. Okay, I'm avoid the lengthy videos, so you can in short span we can understood the concepts, and day by day I'm going to increasing its toughness. Okay, those students not still subscribe this channel, please subscribe. Whenever I'm going to update the video, you can get the notification directly on your mobile. So very, and also I'm very difficult to told every students to go to that channel and see, so you can get directly notification. So please subscribe this channel. Okay, now it starts with the next numerical. Okay, before starting the numerical, we study some formulas we need in further numericals. That is the one is the we need the electric work. Okay, electric work is nothing but it is the product of V into I into E. Also we know that, but V is equal to IR. So the put the value in electric work we can get. Okay, so the electric work equation we can also write I square RT. In previous numerical we see the electric work. Also there is a shaft work is there. Okay, different forms of works. In previous videos I also studied or give the idea regarding the different forms of works. So this is the mechanical work, shaft work. It can be calculated by using the fundamental formula 2 pi nt. Okay, n is the revolution per minute. Okay, T is the torque. Okay, these two formulas also we need. Also we studied every time when system undergoes cyclic process, the summation of Q is equal to the summation of W. Okay, if they ask in exam that either this equation or the data of that particular cycle is satisfied or not, we have to just cross check the summation of Q is equal to summation of W. Okay, when there is in the system there is the interaction of Q W is takes place. Okay, then that system consumes some of energy is called as the new word, that is change in internal energy. Okay, then this for this system the formula becomes the net change Q minus W is equal to the change in internal energy. We can also remember in positive sign also Q is equal to when amount of energy we supply to system, first increasing its internal energy and then we can get W. We either remember in this minus form or also we remember in this plus form. Okay, these are the fundamental formula we need while applying first law of thermodynamics. Well, let's start with the first numerical now. A vertical cylinder with a freely floating piston contains 0.1 kg of air at 1.2 bar. Okay, there is a piston cylinder arrangement containing 0.1 kg air and the atmospheric pressure of that under pressure is under 1.2 bar. And small electrical resistor. The resistor is wired on external 12 volt battery. When a current of 1.5 ampere is passed through the resistor for 90 seconds. Okay, there is a one piston cylinder arrangement. Okay, and that 0.1 kg of air is heated with the help of some electrical coils having resisting coils. Okay, supplied with the 12 volt battery, and the current flowing through that resisting coil is around 1.5 ampere. So resultant that the piston sweeps a volume of 0.01 m cube. Okay, so resultant that we supplying electric work. Okay, resultant that the air increasing its first internal energy, then try to expand, so the piston moves is around 0.01 m cube. Okay, so we can get some mechanical work. Assume piston and cylinder are insulated, are very important here. Okay, and second assumption is air behaves as an ideal gas with CV. Okay, they have given the specific heat of that air, particular air is around 700 joule per kg Kelvin. Find the rise in temperature of air. Okay, before starting the solve the numerical, okay, you have to just that to problem you have to convert it into the grammatical form or diagrammatical form. Has same problem expressed in the form of drawing here. You see there is the piston cylinder arrangement. Okay, an assumption is that first assumption we see that piston cylinder are insulated. Okay, so what amount of heat is developed inside the chamber is not loses its heat to the surrounding because it's insulation. So we conclude that here from that statement where in that numerical Q is a 0, there is no heat loss to the surrounding. There is one hint, the piston cylinder are insulated. Okay, if you observe this numerical, okay, we work on the system. Okay, which form of work we done on the system? That is the electric work. Okay, because of that electric work, what we get, the piston sweeps. Okay, when we supplying the electric work here, okay, when gas expands, the piston moves upward direction, so we can get the mechanical work from the system. Now we get the mechanical work. So is very important, but we need the net change. We supplying electric work and we get the mechanical work. So there is a transformation of energies across the boundary of the system. So we know that in that case we using the formula Q minus W is equal to the change in internal energy. There is a transformation of work. In that case we observe Q is a 0 because the piston cylinder is insulated. So we can get the equation now, minus W is equal to change in internal energy. Here transformation of two forms of works. One work is enter, another work is crosses the boundary of the system. So there is a net change in work is equal to the change in internal energy. Okay. Now we also observe that, see here, the floating piston contain 0.1 kg of air at 1.2 bar. Okay, if you observe in that figure here, the piston expands and contracts, or expansion contraction of that piston. Okay, the upward movement and downward movement of the piston is takes place under 1.2 bar. So it is the isobaric process. Under constant pressure, piston expands. It gives some mechanical work. When gas cools, is moved downward direction. Okay, so that the whole systems work under constant pressure. So we can get the work under constant pressure. Okay, now discuss here. Now we find the net change in work done. First, there is electric work. Okay, I also discussed the fundamental formula. Electric work is VIT. Okay, why it is minus sign, why it is negative, shows because work is done on the system. So voltage is 12, current is 1.5, and the timing is for that 90 seconds. We supplying the current through that resisting coil. So we get work is done on the system is around 1620 joule. Then after supplying electric work, the system gives some kind of works that is called as boundary work, or we just simply say the work done by the system. Okay, the work done by the system is calculated here. Now it is the flow work, or it is the work under constant pressure. Okay, it is the PdV. Under constant pressure there is a change in volume, that is nothing but the flow work or the boundary work. It is the PdV. Pressure in the bar. Okay, the electric one in joule. Okay, have to convert into the Newton per meter. That now the pressure also we need to convert into Newton per meter square. So 1 bar is equal to, we know that relation, the 10 raised to 5 Newton per meter square. So pressure is converted into bar into Newton per meter square, and the change in volume is given. So the boundary work is around 1200. Okay, so the net change. Now the net change is, and this is work done by the system, so it is the positive. The net change, what amount of work is supplied and what amount of work we get. Supplied work is negative, get work is positive. So the net change is minus 420 joule. Okay, there is some amount of work is lost. Okay, we observe here there is around 400 joule work is reduced or losses because that work is utilized to overcome the friction between the piston and cylinder. So that is the minus 400 joules are utilized to overcome the friction. Okay, I also told here that same phenomena here. Now that the minus dW is equal to minus change in internal energy. Okay. So Q is 0, then we get the same formula. Okay, minus du is equal to dW. We can also write the same equation here. Change in work done is equal to, we can supply that sign into that this side. Okay, the dW is equal to minus d. Okay, but our work done is actually, and our work done we see there is minus 420 joule net change is the minus sign. Okay, so that minus sign cancel each other. And we know that the change in internal energy for the isobaric process we calculate by formula. The heat developed inside the cylinder is by fundamental formula mCv delta T. The compare now that change in internal is the mCv delta T. The net change, you know that from that equation we know that mass is given 0.1, Cv is also given. Okay, and they ask the rise in temperature, that is the delta T is the question mark. Change in work done, we know that by using this simple formula we can calculate the rise in temperature is around 6 degrees Celsius. Hopes you understood this numerical. Okay, you can also go slowly in this video. You can get the idea. It is actually now the first law of thermodynamics. The step by step I'm going to increasing its toughness. Okay, and all the numericals from the previous papers and the GATE question papers. Then our next numerical. A closed system undergoes a thermodynamic cycle consisting of 4 separate distinct processes. The heat and work transferring each process are tabulated below. Okay, if we see there are 4 processes in each cycle, 1 to 2, 2 to 3, 3 to 4 and 4 to work. Okay, that 4 processes have the given the values of Q and W. So that the data is consistent with the first law of thermodynamics. They ask the either is this following first law of thermodynamics. Then they ask proceed to the evaluate the net work output in kilowatt. They ask output in kilowatt. Then ask thermal efficiency of the cycle and the change in internal energy. They given the one tabulated form of the each process. Okay, and they ask the 4 parameters. Okay, they given Q and the W in kilojoule per minute. See here, the unit is kilojoule per minute. Find that cyclic process either following the first law of thermodynamics or not. How to check? We just simply summation of Q is equal to summation of W is same. Then either is this is the follow first law. Then ask net work output. Net work output in kilowatt. Then ask thermal efficiency and the change in internal energy. This is the given data, that is the tabulated form. We see here I am purposefully repeat this table in this next slide so you can get the values in front of you. Okay, then now start with the first. Either first law is satisfying or not here. First law, just simply summation of all Q's. Okay, that is a 0 plus 30,000 minus 3,000 minus 9,000 is around 18,000 kilojoule per minute. Similarly, we take summation of W, the work transfer in kilojoule per minute. Okay, see here, this is the summation is around again 18,000 kilojoule per minute. So it is the satisfy the first law of thermodynamics. Okay, then ask proceed to evaluate the net work output in kilowatt. Okay, the net output is 18,000 kilojoule per minute, but they ask in kilowatt. We know that 1 kilowatt is equal to 1 kilojoule per second. Now our work done in kilojoule per minute. Just simply divide the 60. Okay, we can get net output in kilowatt. See here the second They ask net output in kilowatt, kilojoule per minute. Just simply that minute is converted to second. That is 1 minute to 60 second. So it is divided by 60. Okay, then we can get the work done in kilowatt. Third, they ask the thermal efficiency. Okay, the thermal efficiency is the fundamental formula. We studied the thermal efficiency to net work output upon heat supplied. Okay, now the net work output, we know that in kilojoule per minute. Okay, that is 18,000 kilojoule per minute. Okay, we calculate net work output. But now to calculate heat added in the system or heat supplied is very important. They are not directly given. This is the heat supplied. We have to going to find out from that tabulated form. Okay, again now highlighting that values of all values of Q, so we can get the ideas. Is here for the process 1 to 2, Q is 0. For process 2 to 3 is 30,000. 3 to 4 minus 3,000, and 4 to 1 is the minus 9,000. If you are observing these four values, okay, from that values we have to find out the heat added. It's very simple. This is the fundamental. We know that heat added in the system is positive. If you observe these four values, first is a 0, there is no heat addition, so this is nothing, this is not happen, is possible. If you see process 3 to 4 is the minus sign, okay, that is it indicates heat rejected by that process 3 to 4. Also 4 to is also reject heat because there is a minus sign, but you focus on the process 2 to 3 is the positive sign. So from that table I conclude that the heat added in the process is 30,000. See here the 30,000. I also mentioned here heat added in the system is positive. So from the table we observe 30,000 is only positive sign. So I taken the 30,000 heat supplied. This is the very important phenomena in this numerical. And the last one is the change in internal energy. Is very simple. This is a fundamental formula, that is the first law of thermodynamics. From that fundamental formula you calculate the change in internal energy. In previous numerical also we are going to calculate the change in internal energy. Q is there, W is there. By using we calculate the change in internal energy. And we also prove here this is follows the first law of thermodynamics. So there is the summation of change in internal energy. We also cross check. Okay, if you calculate the change in internal energy for each process and further we adding all the change in internal energy, the addition must be 0 because the summation of dq and summation of dw is same here. So by default the net change in internal energy is also 0 for cross checking your answer. Okay, hopes you understood this two numerical, and the next video I am going to increase now the different numericals on the first law of thermodynamics. Thank you.